All right, today we go over half-lives. And so the first question is, if radioisotopes are undergoing decay, why aren't they all gone? And so what I want to get you to get from this slide is decay happens at different rates. And so here we have the decay of uranium. So this is alpha decay, right? Because it's losing a alpha particle. And well, what you have to understand is this occurs at a really slow rate. So if we start with 10 grams of uranium, what we'll end up with is, over time, this will decay. So currently, if we start at the beginning, there are 0 grams of this and 0 grams of this, right? But at some point, it'll start decaying so that you have 5 grams of uranium left. So half of it will be gone. And then you'll have 5 grams of this, right? This thorium. What we want to get across is, for this to happen, for half of this material to decay from uranium to thorium, it takes 4.5 billion years. But if we look at our second example, polonium, for it to convert to lead by alpha decay, it'll take that to go from 10 to 5 and from 0 to 5. So for half of polonium to decay, it only takes 3 minutes. So you'll see that different isotopes have different decay rates. So they have different speeds at which they decay. So we measure this decay using what's called half-life. And so the definition of half-life, is the amount of time it takes for half the sample to decay, okay? And just like we said, uranium-238, its half-life is 4.5 billion years, whereas polonium is about 3.5 minutes. There is a formula, and you can go ahead and copy it down to calculate, for example, the amount remaining or the initial amount. And so here's the formula. So A is the amount remaining. A to the 0 is the initial amount. And then big T is the time elapsed. And little t is the half-life. Now, I think this is kind of a lot to remember, and so there's logical ways to work around these problems. Now, this is also, instead of just remember time elapsed over the half-life time, you can also remember this is just also the number of half-lives. Now, this is a graph of half-life. So this is the decay. And what I want you to notice, the biggest thing, is that it's an exponential function, meaning linear would be something that was straight. So if it decayed linearly, it would look like this. It would be a straight line. But I want you to see that it's what we call an exponential function. And so it kind of gets really steep and then kind of curves off. And so what I want you to know that is in the half-life graph, it's what's called an exponential function. It's really steep at the beginning and then kind of, if you think about it, if you cut half and then another half, every half that you start cutting towards the end is only a small amount. And then let's do a couple problems. I'm going to solve these logically rather than plug it in the equation, but it says element X has a half-life of 2 years. How much of the original isotope remains after 10 years if you start with 4 grams? So if we know that element X has a half-life of 2 years, in 10 years, how many half-life would have occurred. Well, in 10 years, divided by 2 years, gives me 5 half-lives, right? So, right? And so if I start with 4 grams, and here's, after 1 half-life, it would have gone to 2 grams. After 2 half-lives, it would have gone to 1. After 3 half-lives, it would have halved again to half. 4 half-lives would have been 0.25. And then the 5th half-life would have been 0.125, right? So that's how I could solve it. 1, 2, 3, 4, 5 half-lives, so I have 0.125 grams left. Okay. So that's how it could be easily solved. And so you end up with 0.125 grams. I think if you solve it using the equation, you could solve this using the equation. So the original is 4 grams, 1/2, and then you have 10 years over 2. 2 is your half-life. You could solve it like that, and that would work as well, okay? You could plug it in. I'm just going to use the logical way. That way we know, or you understand how this whole thing works. All right, let's try the next one. So go ahead and try the next one on your own, and I'll go ahead and solve it. So the initial mass of a radioisotope is 10 grams. It says if the radioisotope has a half-life of 2.25 years, how much remains after 4 half-lives? So we already know we have 4 half-lives. So if I take 10 grams divided by 2, take a half of it, 5 grams remain. A second half-life would be 2.5. A third half-life would be 1.25. And a fourth half-life would be 0.75. Okay? If 5.0 grams of an isotope with a half-life of 5 seconds is left after 1 minute, how much did you start with? So this one's a little more difficult. So if you have 5 seconds, so 1 minute is 60 seconds, right? So if I divide by 5 seconds, I get 12 half-lives. This one you might want to plug into your formula. You could do this 12 times and just take a calculator and go 5 divided by 2 divided by 2, and you do that 12 times. Or you could say A equals A O 1/2 to the power of TT. And so if we plug this in, this equals 5.0 grams times 1/2 over 60 seconds over 5, which is 12, right? And if we solve that, you would get 0.5, and this is to the 12th power. Times 5. So if I solve this, it looks like it's going to be 0.00122 grams. So that's what it would be after 12 half-lives. But you didn't need to, if you don't want to, what you could just take is you take your calculator and go 5 divided by 2, that's 1, divided by 2, that's another, divided by 2, and you'd have to do that 12 times. And you get the same answer. So it's up to you how you want to approach these problems.